Okay, so question 4 is organic reactions. And once again, definition. 4.1.1, define cracking. So that's when you break up the longer chain hydrocarbons into shorter chains. So officially, you need to say that the chemical process in which longer chain hydrocarbon or alkane molecules get broken down into shorter molecules for 2 marks. That's not a very commonly asked definition, but it's also not that difficult, I don't think. Anyway, we are supposed to solve for x, y, and z. Very mathematical question. If you can see, in the beginning we had 16 carbons and we had 34 hydrogens. Now we have, and if I can just highlight it, we have 6 carbons with Y carbons, and those 3 numbers need to add up to 16. But obviously there's even more that we need to look at. I think maybe if I write it out like this, it'll help. CYHZ, there's a 2 in front here. So there's a CYHZ and there's another CYHZ. So if we just look at it like this rather, basically 6 plus 6 plus y must be 16. Because we have a total of 16 carbons, that is equal to 6 plus 6, plus 6 plus 2y. So that means that y is equal to 2. Because 6 and 6 is 12, which means you have 4 left over. And if 4 is 2y, it means that y is 2. So now, if we draw out a 2 carbon thing, we can try this. We can see that when it's cracking, it takes long chain hydrocarbons. This is a hydrocarbon because it is CnH2n plus 2. It's C16H34. Now, CYHZ, H is either going to be a 4 or H is going to be 1, 2, 3, 4, 5, 6. So, not H, sorry, Z. So Z is going to be 6 or Z is going to be 4, depending on what happens with this X over here. If we have 6 carbons, we have other options, but the 2 carbon one only really has these 2 options. So if we just want to check quickly, the total number of hydrogens is 34. So 34 hydrogens is equal to 14 plus X plus Z plus Z. And Z must either be 6 or 4. So let's see, this would be 20 is equal to X plus 2Z. And Z must either be 6 or 4. So if we just check those 2 options, so this is very maths. I mean, there's very little chemistry going on here. But if Z was 6, then X would be equal to 8. Because 2 times 6 would be 12, and 20 minus 12 is 8. If, however, we had Z being 4, that would make, if I just write it out again, X plus 2Z, that would make X equal to 12. Because 2 times 4 would be 8, 20 minus 8 is 12. Do I want X to be 8 carbons or 12 carbons? Which one is more reasonable for what I'm doing? What happens with cracking is you make alkenes and alkanes, typically. And C6H8 it's not an alkene, it's not an alkane, it's not even an alkyne. If you know, alkanes are CnH2n plus 2, alkenes are CnH2n, and alkynes are CnH2n minus 2. So for this one, it's not an alkane, it's not an alkene, and it's not an alkyne. 8 is not going to be an option, which means we need Z to be 4. Z must be 4, and Z being 4 makes X 12. That was extremely maths and not very much chemistry at all. I'm sorry if you didn't follow it, but basically rather than guessing, we just tried both scenarios, and if it's C6, so if I just draw quickly, 1, 2, 3, 4, 5, 6, and it's 1, 2, 3, 4, 5, 6, 7, 8. Every single one of those carbons is missing a hydrogen. That is too many carbons that are missing a hydrogen. If this thing only has 8 hydrogens, it's not going to work. If it has 12, I can add 1, 2, 3, 4. I can put a double bond in there, and that's fine. That works. So C6H8 is not possible because there are not enough bonds to satisfy the 4 bonds per carbon rule. So a whole bunch of algebra happens, and you just hope like hell, and eventually you get the answer that X is 12, Y is 2, and Z is 4. So now, if we look at the next one, they're doing complete combustion. So, complete combustion, I just want to give you a few guidelines on doing this. Basically, they're saying write down the C6H14. The complete combustion, what happens is, so this is where you start. You add oxygen because it's burning, and it makes CO2 and H2O. I'm going to tell you now, you start with the hydrogens. The first thing that you balance is hydrogen. The second thing that you need to note is H2O must be even. Now again, you don't have to listen to me, but this is the quickest way to do it. If you have an odd number in front of the H2O, you double it to make it even. So you double the odd coefficients to make it even. Okay? So, and then after that, you balance the carbons, and then last, you balance the oxygens. So let me just show you quickly, and it's a bit dumb because I have the answer there, but here, in order to do this, I need to put a 7 here to make 14 hydrogens on both sides. You start with hydrogen, but I've just told you that mustn't be an odd number, so I need to double it. So I'll make that into 14, which means I need to make this 2, because now I have 28 hydrogens on this side, and if I put a 2 in front here, I have 28 on this side as well. Next, so now I've done that step and that step. The third step is balance the carbons. There's 6 on the left. There's 12 on the left, so I need to put a 12 there. And now the oxygens is a bit tricky because there's a number here for oxygen. There's 24 oxygens there, and there are 14 oxygens here. And so that together makes 38. So that means I need to do 19 oxygens here because 19 times 2 is 38. You start with the hydrogens. You make sure that the H2O is even by doubling the alkane. Then you balance the carbons, and then you balance the oxygens. Every single time you get asked those questions, you follow those steps, and it will. You can do it any other way. I think that's possibly the quickest way of doing it. And we don't really want to waste time with nonsense, although that is 3 marks, so it is maybe worth doing. You get 1 mark for the left-hand side, 1 mark for the right-hand side, and then 1 mark for balancing it. Okay, next question is another definition, if you can believe it. What is a positional isomer? That's basically the numbers are different. So it's the compounds with the same molecular formula, but different positions on the side chain, substituents or functional groups on the parent chain. So it's the difference between butan 1-ol and butan 2-ol. Still 4 carbons, still an alcohol, but the number has changed from 1 until 2. That is a positional isomer. So you can have pentan 2-one and pentan 3-one. 5 carbons because it's pent. One means it's a ketone, but the one is 2 and the one is 3. That is a positional isomer. Functional isomer, there's only 2 examples. Esters and acids, and ketones and aldehydes. Functional isomers, there are only 2 examples. Esters and acids, and aldehydes, and ketones. Chain isomers, what happens is you change the length of the longest straight chain of carbons. So that would be hexanoic acid. It's got 6 carbons in the longest chain. Or, for example, 2-methyl hexanoic acid. Pentanoic acid. So hex is 6 in a row. Methyl pent is 1 carbon added onto 5 carbons. You can also do butane. Butane is 4 carbons. Or you can do methyl propane. So butane has got 4 carbons. Methyl propane is 1 added onto 3. It is still 4 carbons in total, but the main chain length is different. So you can have, you can have octane, which is 8 in a row, or you can have ethyl on hexane, which is 2 on 6. So you can have a whole lot of different things, but basically the functional isomer, ester, acid, or aldehyde ketone. That's it. Chain isomer is you change the length of the longest straight chain of carbons, and positional is you change the numbers. Same functional group, same number in the longest chain, but the number is different. That is butan 1-ol and butan 2-ol is a positional isomer. Okay, the type of reaction represented by reaction 1. So this I would like to try and show you quickly. Basically, if you have 2 reactants making 2 products, or 3 reactants making 3 products, or 4 reactants making 4 products, but typically it's 2:2, that is a substitution reaction. That is a substitution reaction. If 2 makes 2, it's a substitution reaction. If you have 1 making 2, if one thing makes 2 things, if you increase the number of things, if you have 1 reactant and you end up with 2 products, that is elimination, just as a rule of thumb. And if you have 2 things making 1 thing, that is addition. And I shouldn't say thing, but if you have 2 compounds reacting together and you end up with 2 compounds as products, that's a substitution reaction. If you start with 1 and you make 2, that's an elimination reaction. And if you start with 2 and you make 1, that is an addition reaction in general. The other option is substitution reactions have no alkenes. There are no alkenes in a substitution reaction. An elimination reaction, you make an alkene. So typically you take something off of an alkane and you end up with an alkene and water, or an alkene and an alkyl halide. You end up with 2 products, one of them being an alkene. So the alkene is the product in an elimination reaction. And in an addition reaction, the alkene is the reactant. So if there are no alkenes in the reaction at all, it's going to be substitution. If there's an alkene as a product, it's an elimination. And if there's an alkene as a reactant, it's an addition reaction. So this one over here, this number 1, I just told you it looks like a substitution because 2 things make 2 things. However, and again, sorry to say it like this, but I thought it was substitution because 2 makes 2. However, this thing over here is an alkene. I can see because of this part here, there's not enough H's, which means there's a double bond in there, which means that this is not 2 products, it's just 2 versions of the same product. So the one is going to have the chlorine on the 3rd carbon, and the one is going to have the chlorine on the 2nd carbon. So it's 1, 2, 3, 4, 5 carbons. The one is going to be 2-chloropentane, and the other is going to be 3-chloropentane. Anyway, so 4.2.2, they want the type of reaction represented by reaction 1. So I thought it was substitution, but if I use the alkene test, or whatever you want to call it, this thing over here is an alkene, and it is a reactant, which means it is an addition reaction. You are adding HCl, you are adding a hydrogen halide, you are adding H and Cl. So that you're making an alkyl halide. It is hydrohalogenation. If you want the full name, they'll probably accept it here as well. It's hydrohalogenation. So there they say it's an addition reaction, it's hydrohalogenation or hydrochlorination because you're specifically adding chlorine. Then they want the structural formula of compound B. This bloody question 4 is normally quite tricky. But anyway, the structural formula of compound B. So now you made A and you made B, and I told you one of them was going to be 2-chloropentane. The other one is going to be 3-chloropentane. So now at this point, they took A. So they took A, and here they added an OH, and it got added onto the second carbon. So this must be 2-chloropentane, and this must be 3. So what we want to draw for the structural formula of compound B, we want to draw 3-chloropentane. So there it is, 3-chloropentane. And so if you get a mark, if you have a chlorine anywhere, if you get a mark, another mark if the chlorine is on the third carbon, and then you get a mark for the rest of it having 5 carbons and all of its H's and things. Then for 4.2.4, they want to know what is X. So A was 2-chloropentane, 5 carbons with a chlorine on the second one. Now we added water, and here also they're being sneaky. They're making it look like there's one reactant, but strictly there's 2 because water was added as well. This is a substitution reaction. This is hydrolysis. And you put on the OH and you take off the Cl, so that thing there is going to be hydrogen chloride or HCl. They're asking you for the formula, so you cannot have hydrogen chloride as your answer. Hydrogen chloride is not a formula. The formula is HCl. Then for 4.2.5, they took what they made in the second reaction, and they're asking for the inorganic reagent for reaction 3. What you've done here is you've removed water. This last one is an elimination reaction. You have removed water. You have made an alkene. This is an alkene. So you started with an alkene. That was addition. You made an alkene. That was elimination. In this one here, there are no alkenes, so the one in the middle is a substitution. It's an addition reaction, a substitution reaction, and then an elimination reaction. And in order to dehydrate something, you need H2SO4. You need concentrated sulfuric acid. You can also use phosphoric acid. But sulfuric is normally the one that we know about because it's the one that we use for esters to do an esterification reaction, which is also an example of a dehydration reaction. Then they say that compound A, which was 2-chloropentane, can be converted directly to the organic product of reaction 3. So you can go straight from something with a chlorine on it to something with a double bond. That would be dehydrohalogenation. You're taking off the Cl and you're taking off the hydrogen. What else do you need besides heat for a dehydrohalogenation reaction? You need a concentrated strong base, or specifically NaOH. And they say write down 2 terms that describe this type of reaction. I would imagine it's going to be dehydrohalogenation and elimination. See, there they are. So the name of it is dehydrohalogenation, and the type of reaction that it is elimination. Unfortunately, guys, reaction rates is quite a lot of theory, but if you can just get the general thing of where the alkenes are, you would at least be able to get the addition, substitution, and elimination marks. And typically, if they ask about a reaction condition, just say heat, and otherwise it's H2SO4 for dehydration, and dehydrohalogenation, you need a strong base, a concentrated strong base.